has a number of phases. The first phase, and one of the most challenging, is exploration. That's basically trying to find a new area and determine whether it has oil or natural gas. It's an area where geologists and geophysicists have the most to do with what we do. But once we drill an exploration well and determine that there's oil in place somewhere, the next part of the job is actually to appraise the oil and gas reservoir and figure out how much oil and gas is there and figure out whether it's cost effective actually to produce that oil and gas. And then the next phase is production. And when I worked as an engineer, I was a production engineer. And there's an incredible amount of work, incredible amount of engineering that goes into determining how to produce an oil field, where to drill the wells to produce the field, and how to design the equipment to produce the field. And then from there, once we produce the oil, it goes on to the refinery. And we have a huge refining industry in this country, and then on to marketing and gas stations. But I'm going to start with producing the oil and finding the oil. One of the things that, when we talk about oil, we talk about pools of oil. And we use language that, makes people think, well, there's a big, like swimming pool, a big hole in the ground, and it's filled with oil. It's not that case. Oil is actually contained in tiny little pores in rock. And so, just like a rock you pick up off the ground, a piece of sandstone, this is a sandstone, and what you see is that there's a void space in between the sand grains. And that's where the oil is. Those sand grains, when they're compacted in the ground, they start out with water in the area between the sand grains. Over time, if things are right, or if the conditions are right for it, oil may replace some of that water, and that's where the oil is found. There's a really perfect picture of how this works in the East Texas field, which is about 120 miles east of here, in Gray County, Texas, around Kilgore. It's an incredibly productive formation. It produced 4.5 billion barrels of oil. It's been producing since the 1930s and is still producing. It's a sand formation like this, a sandstone formation like this. It's got about 25% porosity. And so the void space between sand grains makes up 25% of the space. And that porosity is important. It's one of the things that petroleum engineers like myself need to know about the formation in order to produce it. Another thing that we talk about a lot is permeability. The East Texas field has, the unit is called Darcy's. It has 3 Darcy's of permeability, which is an incredibly permeable formation. So if you were to take the core of that sandstone immediately from 3,000 feet below the surface, or 2,500 feet below, which is where that sandstone is, and bring it to the surface without reducing the pressure until you got to the surface, what happens is you would see oil oozing out of that sandstone because of the pressure inside the sandstone. How quickly that oil or water or whatever fluid is in there can move through the sandstone is the permeability. Some of these easy wells or easy oil fields to produce, like the East Texas field, they've all been discovered. They had good porosity and good permeability. The formations that we're producing today are typically not anywhere near this good. They've got smaller porosities, anywhere from 5 to 15% porosity as opposed to 25% like the East Texas field. And they've got, whereas the East Texas field, we measured the permeability in the Darcy's, and they had like 3 Darcy's. We've got millidarcies, thousands of Darcy's that we're measuring in the permeability of formations now. So it becomes more and more difficult to produce the oil from the fields that we're discovering now. You can sort of picture this, and when we do this, when I was a young student in college, the way that we kind of looked at this was we just filled a cup of sand and poured water into the cup. If you've got a cup of sand, there's still a lot of space that you can pour the water into. And what we do to actually measure the permeability, how quickly fluids move through the rock, is we cut pores from deep underground, and we take them to a laboratory, And we try to force fluids through the rock. We try to force oil through the rock. And we look at how quickly you can force oil from one end of a piece of core to the other, and that's how we measure the permeability. So this is a very traditional look at a hydrocarbon reservoir. You see the blue here is water, the green is oil, and the red is gas. And that's how it goes in the reservoir. It always separates out because the gas is lighter than the oil, and the oil is lighter than the water. And typically, in any kind of reservoir, you've got to have three things, three types of rock. You've got to have source rock. The source rock contains plant and animal matter that was laid down in the ocean when the rock was deposited, when the soil was deposited, the shells and sands and whatever. And that gets buried deep underground as more sand and more shell and more other types of rock are deposited on top of that. But that's the source rock. You know, hydrocarbons are really, chemically, it's very simple. It's just carbon and hydrogen. And it comes from cooking plant and animal matter underground for many thousands of years. Well, the source rock gets cooked under high pressure, under high temperature. And the second kind of rock you have to have in order to have an oil reservoir is a reservoir rock. A rock that has enough porosity to hold the oil. And so the source rock for this type of trap may be right down here or below. The oil and gas percolates up through the various rock formations to this reservoir rock. And so that's got enough void space to hold the oil. Now there's one third kind of rock that you have to have, and that's a sealing layer, a sealing zone. To have an oil reservoir, you have to have some type of layer up here above the reservoir rock that is impermeable enough to hold that oil and natural gas in place. It's typically a shale formation. Now this is an anticlinal trap. Sands and carbonate zones that are very deep underground. The land bubbles over time and forms various kinds of traps. This is kind of like an anticline, kind of a dome underground. Here you've got, on this other side, you've got a trap that was formed by a fault, by shifting rock from a sandstone, shifting it up against the shale zone. You've got to have these kinds of traps, and that's what people look for. That's what geologists look for in looking for oil and gas. Years and years ago, when we first started searching for oil and gas, geologists looked by looking at what was going on the surface. If they saw a hill that was just out in the middle of a flat area, that hill might have been formed by a salt dome or something very deep in the ground, and that's where they would drill for oil. It was as simple as that. If they saw a fault, they would try to figure out where the fault was going down in the ground and try and figure out from that where to drill for oil and gas. We're much more sophisticated now, but that's how geological prospecting got started.